Good afternoon, gentle readers. It's November 2024, and today is another episode of Logos 2000, a study in foundations of philosophy, of reason, logic, mathematics, physics, the natural science, and to some extent statistics and probability theory. He's forming kind of a coverage of foundations, these foundations of our reason and our theory, which for some philosophers is one of the uttermost goals of comprehension and understanding, that it's associated with the greatest sort of thought experiments and the comprehension of matters of intellectual fact. So to that extent, it's kind of grandiose and a bit ambitious. And the idea that there is one, a foundations, it's plural, the term, but it means a singular thing, that there is one is even itself a matter of some incredibly extended discourse over many centuries by many brilliant people who have given to us via library and academia, and even furthermore the stories of experience and the stories of the epistemology and the semiotics of meaning of being, the stories, then that each person has their own incredible individual experiment themselves of what that is. So today it's to be a little bit more about mathematics with some wandering or meandering about philosophy, because there's a language of a philosophy and a philosophy language, and there's a language of a philosophy of science, and there's a language of philosophy of mathematics. And kind of as we were reading from Collingwood an episode or two ago, it's not always the case that mathematics and science are considered the same thing. Whereas other times it's kind of suggested by some theories of science, not all of them, but some great ones, that there is only science, that there's only scientism, and there's only logical positivism, and this is all that can ever possibly be granted to be within the domain of reasoning. Now this, of course, is entirely opposite or contra. Those who have that there's objects of the mathematics are only available to reasoning. They're not scientific objects, they're platonistic objects. So that just affects to reflect that there's a big difference perceived between logical positivism and mathematical platonism. Logical positivism being that it's just a theory and on so few words, and that's all it can ever be. And mathematical platonism is that there's some objective of universal ideals that are always existent and the same for everybody to figure out. They don't have to be different. They can really be kind of one combined theory then that takes apart and pulls together these things. Some of the readings here have been from Bernard d'Espagnat. He's on philosophy and physics. And he, as I put it, is a grandiose hedge, and he's also kind of a timorous grandiose hedge in a sense, while at the same time as he contemplates and then knock about these ideas of realism and anti-realism or fictionalism in physics for the instrumentalist and the operationalist viewpoint, and an inner subjectivity and towards a realism that he's a great hedge. And then Cassirer was being read here a bit, who's from about 80 or 100 years before, and as well, this is after logicist positivism had kind of be a thing, and even to where it was like claiming a priority and even saying that these ideas of the greater metaphysics at all or mathematical platonism at all didn't even exist. It's perfectly suitable in logicist positivism to have a multiverse where all these things exist that can never possibly be, but it's just kind of an extreme that in some aspects or versions of logicist positivism there's nothing can really exist except, a facile sort of, for some kind of not satisfying these things. So Cassirer was kind of helping explain how there's a whole theory of science, at least attached and associable with that. And Descartes is kind of bringing that back together. He's like, we got to have a realism somewhere. And then it has to be as according to this part of the science and according to our practice of the theory of science. Not me per se, but scientists. Being a theoretical physicist is a lot easier sometimes because it's all true and false, and it's not necessary to try to figure stuff out via experiment because it's all provided by the theory. And so that's pretty thoroughly explored here, vis-a-vis always getting things right, and you know, the individual experiment of like keeping oneself in one piece and you know, upright and these kinds of things is another. So this other guy I've been reading a little bit is Schopenhauer. And so Schopenhauer is hundreds of years before this. But in the time after Descartes, where Descartes had some great benefits from being right in the middle of Suarez and the Jesuits, who gave him his education, and Mersenne, who had a connection to the pulse of what would be received according to the authoritarian doctrine and dogma of the day, and as well with somebody like Arnauld. So Arnauld. Arnauld is a great philosopher at the time of before Descartes, but like after the medieval times, and so Arnauld is received as really one of the greats. So if you were to take Descartes and then just kind of set him aside and only had Mersenne and Arnauld and Suarez, then what you'd want is somebody like Descartes to kind of help bring that all out and bring that together. And he's a hedge. He entertains that, like, for example, that there's a strong strain of logicist positivism, yet as well that in the philosophy of mathematics that there are the real things, that there are the objects of mathematics. So I was reading this from Copleston, who's a historian of sorts, and so next to Schopenhauer then that Copleston just kind of gives a summary of this, but Schopenhauer is another great grandiose hedge, and he really picks up and puts down a lot of these notions, and then he's held up as like a great hero of the post-Hegelians and these types who just want to have everything to be kind of detached from any other dogma or determinacy, and to have kind of a replaceable dogma, a replaceable determinacy, a replaceable deism. I mean, religion isn't necessarily a matter of belief in the supernatural. It's only whatever people bind themselves to at all. It's whatever the ontological commitment is. That's what we're legis to. Related in this way, and to each their own, and it goes without saying that everybody's got their own theory, but a lot of them share many common beliefs, and when they learn of theory of people who are successful with their theory, adopt it whether or not they know what it is. And then the idea of being able to make this great ontological commitment to a theory has, for reasoning beings, that it's got to be fundamental in the foundations and fully explained kind of from all the way up, from the ground, the solea, or the grund, the ground, or the foundations. So here then it's mathematical foundations and logical foundations. So for logical foundations, it's like, well, as long as it's a modal logic, meaning it's always a constancy everywhere, and everything is determined according to one universal modal, then that's considered strong logic. It's considered correct. It's considered resistant to meddling and ambiguity, although that depends a little bit. To be modal. And then temporal, the idea that temporality is that any one given time, only everything is kind of like so. And that includes the ideas of like the judgments we make, like is a poor judge of character a moneyless judge with character, or a bad judge who though judges character. These kinds of things, just reflecting that there's a temporality, the modality, what makes contingents, and then those for the theory of logic later show up as contingents in the theory of physics. to be what will be according to what may be, and then what is. Only just so saying that for logic there's this modality, and then the other part of logic is the relevance logic, that which speaks to that which it relates to, and the two things that don't otherwise relate to each other do not say anything logically about each other. And then one may, if one would assign something a certain priority as saying this is what we can consider now and here and not irrelevant things, that's its own relevancy. And so they're associated so utterly, eventually, in some completely connected relevancy. But as with regards to the predicates and propositions of objects with regards to each other, those things that which are not related to each other say zero about each other, except in some universal connection or any wider connection where two things can be related, however so happenstantially, that it's not so necessarily so that they are otherwise having to keep any of this kind of meaning as it is. So then there's mathematics. For thousands of years and still today, mathematics is geometry. It's the world measure. It is, for all practical purposes, the continuum analysis. And then the algebra and the theory of words is an analysis of individuals and the discrete. So you have the discrete and the continuous, the analog and the discrete, the finite and the infinite, in a sense. And so geometry is considered the classical mathematics. And algebra is made for anything to do in the finite combinatorics or words. So number theory is kind of included in that. And that they come together. Here it's established that mathematics is these things. It's geometry and a number theory. There is about it arithmetic, algebra, and analysis. And two of the most relatable and relating things are function theory and topology and an operator calculus. And that those then make for that logic has terms, predicates, and relations, or terms, propositions, and relations, or just propositions that plainly syllogistic, then a wider end deductive and deductive inference. It's got terms, predicates, and relations, or terms, propositions, and relations, the logic. And mathematics has got about all that it needs in geometry and number theory. Then for analysis and methods and synthesis, the arithmetic and algebra and analysis. And then for these matters of the flexibility, often that the function theory, topology, and operator calculus, because everything else is well defined in terms of what's standard and finite and completable and completed in these theories, vis-a-vis when they run out at the ends and their measures and they don't relate, and so it's independent how they could relate, and that they relate then in multiple ways, or as regards to conjectures independent standard theory. This usually held up as whether there's a prime in infinity or not, or if there's a point in infinity or there's not. Meaning then that the numbers as so infinite either have that there is like a last prime, and so that it would be fundamentally able to divide something all the way down, or there's not. And so that there's an infinitely divided, whether there's an infinitely divisible, which is standard, the delta epsilonics and all that, or the infinitely divided when there's atoms. These being standard infinitesimals. Iota values is what they're called here. Both exist, yet neither attains to the other, only in the limits that either to complete, and the other is said that variously, according to some weak accounts, that it doesn't, but who cares? Now, I'm being kind of facetious about that because I'm trying to put it in a bad light so that rhetorically it'll be associated with a little bit different of an account than it's often given today as just kind of like, this is what everybody thinks, because it's not. That then, with regards to, if only in my personal and humble opinion, as it so may be, or my personal opinion, that there is this wider discourse, and it's better. It's a fuller mathematics, and it's not inconsistent. It's better. So that's just kind of why it's to frame these in these completions, and why it is that the deductive account has to be entertained to arrive at that. Otherwise, an inductive account can never complete its own infinite completion. But that there is an infinity can. And then it has to be its own kind of separate thing. So logic is kind of this way, and then mathematics is kind of this way. And then for foundations, oftentimes you'll see arrived at something like a theory with one relation. And so this is usually set theory. So it's like a logical theory with mathematics, and everything in mathematics is built up that according to model theory as being models and structures of those things of the objects of geometry, of the objects of number theory, of the objects of arithmetic and algebra and analysis, which I've usually been just leaving out analysis and just said arithmetic and algebra, and then later saying operator calculus is everything, and that being analysis. But that analysis has its own opinions and stipulations and the various approaches and the subfields and what's standard, and according to the complementary duals, what is standard and non-standard with respect to either way. That thusly this set theory is a theory with there's only one relation in the language, and so that gives nothing but all the combinations of what those can be. Then descriptions are attached to this later, definitions introduced, in some cases stipulations, like stipulating that points can make a line when they can't. Like when David Hilbert introduced a postulate of continuity, he says, well, now that we have point sets in our topology and we want to make those lines, we only want to have one elementary element, points, and so to make those points to be a line, then it has to extend and be fully end, make the property, the least upper bound property and gaplessness hold true. Well, then that's just kind of a feature that's not part of set theory per se, but it's part of the descriptive account sitting right above that. The descriptive set theory is really descriptive number theory, or descriptive geometry, or descriptive arithmetic, or descriptive algebra, or descriptive analysis in set theory. It could be another way around. It could be part theory. It could be ordering theory, or it could be maybe some combinatorics. All theories with only one relation, framed variously. And then with regards to what that means, all the possible ways that can be, and then when there's introduced things that to put a stop to, otherwise that would make it so that some very simple things fall out of it, that they would just be just one side of this two-sided thing, the half-truth. So this is usually just put up as that there's a Zermelo-Fraenkel set theory, and it establishes a great account for a standard sort of infinitary reasoning that's not really given in infinitary reasoning, but it gives cardinal numbers as having a exponents and establishing an inequality, and then with regards to relating those to the real numbers of a usual sort, the Eudoxian way or an Archimedean way, and then delta epsilon x, which is so great, and it gives the fundamental theorems of the calculus, the integral and differential calculus, that otherwise it would be lacking, and it would be easy to drive a contradiction in it. In fact, some people still do, and then it's all got to get fixed again. And so then that has for the objects of mathematics, it's like, well, if we're going to have a continuum be primary in the theory, then it exists these various ways. It's like a line segment, just point A to point B, the postulate of continuity of David Hilbert, a line drawing, the missing piece from geometry, where when you're told, according to classical constructions, that lines are never drawn, they just kind of exist between any 2 points. That then the actual practice of it is like, well, I drew a line here, so this is the way it is. That is line reals, these iota values, a different mathematical model of a continuous domain than field reals, the complete ordered field, often is after Archimedes and Eudoxus and Cauchy and Dedekind for Weierstrass and delta epsilon x, which makes our great approach to all kinds of numbers after the rationals, that the rationals are so large and dense in the real numbers, like the Pythagoreans said, is like there's nothing else. So for the Pythagoreans, it was all rationals, and anything left was like, that's not our boat. To these days, it's like,
Well, the rationals are countable because we can at least line them up and make them as according to counting numbers. So the reals are uncountable. So then in that case, in modern mathematics way, almost all the numbers are irrational. So there are various accounts of why it goes either way for mathematics, and so it's necessary to really make for an account as to under what conditions of what acts, what opuses, what works, what fates we make in the geometric or in the algebraic or in the analytic of these settings, what synthesis arrives from results, that there's these continuum mechanics. So that in the theory, the continuum itself is primary, then it's arrived to it by these various finitistic means, and that includes line reals and field reals, and then signal reals, which is that from that the rationals are so dense, and then that more than them is enough to make a real continuum again. It's signal theory from the signal reconstruction theorems of the 20th century, really, of Shannon and Nyquist. So after Fourier made Fourier analysis and let's take a bounded segment and we're going to have an infinity of integrals in a row and add them up, a reductio and then another reductio, somehow having done that, and it's non-standard again. As much as calculus is non-standard, then the Fourier-style analysis has got its own justification to provide. And it's been addressed here pretty thoroughly. And then there's the Shannon-Nyquist, and this kind of sampling theorem is over something that would have to be rational and meet all these points according to the denseness and filling all the rational or algebraic roots. It's countable, but it's rational and algebraic. This is this third kind of a continuous domain, which mathematics you can build one and is integral to signal theory and the limit, and it's kind of like super standard, extraordinary, but it is as well a thing. And then these follow this between first was the counting numbers 0, 1, 2, 3 through infinity are enough to say that that's an integer continuum, because it's got a point at infinity and it's infinite, and then whether or not those are finite all the way through it's independent. Standard number theory, which just starts counting from 0, 1, 2, and 3 and onward forever, for pianos and Pressburgers, the models of addition and multiplication of natural integers, that the integer continuum is and that. And then the long line continuum is after Du Bois-Reymond, 19th century mathematician who, in the decades before set theory became a thing and before Fourier-style analysis became rigorous as it is, a standard account, had established that all the expressions in real valued formulas would be even more than there are of the real numbers, countable and uncountable again. So that's its own kind of contradiction when it's but those have to be of those. It just kind of the reals and rationals, well, that gets into the domains and the functions and how they could be. And just an infinitude only between 0 and 1, that's extraordinarily small. Yet it's close enough to be continuous that you can say it's not different. They used to have their standard ways as well to establish why it's continuous. Vis-a-vis having one formalism and a foundations altogether, that the one we have is kind of a given course up a track. Looking at a mountain and there's these 3 different approaches to get up the mountain. Well, they figured out how to make the one way up, and then it's kind of been advertised after that. It's people fall off the other ones, so don't try it. Well, it was there. It's there. So that's kind of a part of the approach to the mathematics, and that all the objects in mathematics kind of are of those. And then they all exist because one of them exists, and it's got all of those. So that's mathematical Platonism, that they all exist. And then the logicist positivism is make as small and brief a theory as you want. Talk about only the numbers 0, 1, 2, and they go around in a circle. Z2. A finite ring with 2 elements, 3 elements in it, integers. That's a perfectly consistent theory.
and it's a perfectly complete theory. It's not the theory of all the objects of mathematics, but it's all that you have to. You don't need the whole theory of the objects of mathematics to make any old theory at all. That works great. It works fine. It works perfectly well. It's only when we get into these infinitary expressions and reasons to care that then we'd have to have this greater theory at all. And what people in foundations want is like the whole thing done. And then similarly, when we get to these laws of large numbers, which are not standard, which are super standard and extraordinary, and have real analytical character throughout and afterwards, and only available through real infinitary expressions, then that offers the possibilities of things that can actually result mathematics that's real and is of these acts, these opuses, these works, these fates in the continuation and individuation, the completion and the making of discrete, or the quantization of these kinds of things. Often most familiar as quantization, and making a quantum particle that is a finite amount that can be summed back up of what otherwise are continuous quantities related together by as how they are. So this is mathematics, and then physics is pretty familiar as well. It's physics. It's the theory of how things in the real world, as it may so be, that they have a theory that according to the theory that you can design a thing in physics that according to the theory it will behave as according to the theory details and describes how it will behave. And then that's according to reproducibility of experiment, measurability or observability of the experiment, and falsifiability of experiment. That if you can make it so that when you know the limits of the theory, that you can put something outside that and show that it changes the thing, falsifiable, and that otherwise that's the kind of thing. And then that's stacked up quite a bit in terms of the operationalist and the instrumentalist views that somehow it must be that the mathematics that arrives at the very, very few things, or the very, very faint things that we can see in the sky survey, or as after the particle mechanics and the visible, the microscale and the macro scale, that then the statistics that come to build this also gets involved in all the things. What is actually being seen and observed, and it's just kind of like the end of a stack of other experiments, falsified, or not again, that arrives at then when something's said to have been stood up and holds good and held up as kind of a reference model of a theory that at least holds up good, looking for other things that fall out of it, helps to explain why sometimes it's said that theories are like the laws, or that they hold up all the time, when really it's also sometimes that they don't. And when they don't, then it's whatever are the effects underneath that. Then it needs to be isolated, the configuration energy experiment, actually in terms of what these effects are. So that just goes to show that things are evaluated according to what kind of data there is of them, and the common wisdom and these various correspondent and coherent and pragmatist theories of truth, what people believe to be so. And so then besides that, without a further account, and I'm not yet talking yet really about how a strongly mathematical Platonist account can make a mathematical universe hypothesis to show and give why, according to a theory, that there is 3 space dimensions, an array of time, and also kind of things about things in it. That there was, a great deconstructive account of mechanics, and that being a primary concern of the physics, of course. That as well, just like the little theories of logicist positivism and nominalist fictionalism in mathematics, that can be assembled and dispatched for all practical purposes. Then in science, it's like kind of a last little theory. It's like nothing's really for sure through all this kind of stuff. But then by holding at least one thing it fixed, then we can take out these partials of it. So the statistical hypothesis and all these kinds of things are so partial. The partial differential equations, the whole analysis thing, are so partial. The numerical methods and the small angle approximation, so partial. The electron physics and a quantized view of a continuous thing, again, so partial. The severe abstraction of a mechanical reduction, so partial.
So in terms of the completions, then it just makes it kind of tough to figure out what that is in science sometimes. Yet at the same time, when it's all lined up, it's like, well, we kept everything else constant, and then we're able to figure out that something is pretty much as perfectly accurate as in the order as of the atom is smaller than us. And that's it. The 25 orders of decimal magnitude. And then that is figured that's perfect. And it gives something like in the gigahertz scale, or otherwise in terms of precision of devices, they can be planned and they show up in the right thing, just like making a musical instrument with strings of a given length and thickness and resonance and this kind of thing. That merely by the design of the experiment, it can be arrived at the properties of the results of the outcome of the experiment, reproducibility of the experiment. So that said, though, with that being empirical altogether, then the theoretical is still always being held up as what provides that. And then for the weak logical positivists, they're like, and then we forget where our theory came from. And it's like, don't you want to know where the food and the theory comes from, and be sure that it can take into account these things? And for a lot of people, it's like, no, it's already proved what I wanted it to say. And so I'm happy with it. And it's like, well, actually, it just didn't disprove what you didn't want it to say, which is all you can say science said. And then it's like, well, that's for philosophers. We're physicists here who compute. I'm like, well, are you really? That just reflecting on the whole Chinese room comment the other day, or with regards to whether people are, it's sometimes used as a put down, and to say whether somebody in physics is really doing physics or whether they're just following the color by numbers and the connect the dots, which somebody has to do. But the idea is that the physicists should also have enough philosophy to know the theoretical besides the empirical of their fields. Otherwise, it's matters for technicians, operators of sorts, which are often much more critical in their actual capabilities and experience and practice after the fact that the numbers and the configuration energy experiments are given. Well, let's see then. Let's find some mathematical works and take a look at them and try to extract something from them. So we talked about Cassirer and D'Espagne and Schopenhauer a bit with regards to and Descartes a little bit with regards to their theories of mathematics and for the theory of the philosophy of reality and the theory of philosophy of the science and the physics. And there's so many different applications and algebraic manipulations and the implicits and everything, then that finding something that ends up being a simple formula is deemed of great and profound importance. And then that it has to arrive at stuff like the Fourier-style analysis, an infinitary expression, non-standard again, its own justification after calculus analysis, it's standard again, its own justification after these models continuum, which by now people have long forgot to care or think or even believe that there could be any alternatives at all, because it's just been reiterated that it's always been the case since instruction began of it in their career and education. That would be so. That looking back, of course, over the whole thing, that most of these things were decided thousands of years ago by Aristotle, as largely that being the canon and everything about the Aristotelian as matters of reason and picking either side of a two-way thing. Then that as well, that's still all the same things that arrived at all the superclassical concepts like atomism and particle wave duality, which is kind of super standard and super standard again. That helps to explain why that's so relevant to make sure that when it's trying to be uncovered and discovered what's wrong with science, because something's so wrong with it that it's 120 orders of magnitude wrong between general relativity and quantum mechanics, for example, premier theories of the day, because one is all held up and it's held up as a reference setting this way, and the other one is this way, and they disagree. For then what energy and configuration experiment is relevant into each of them, And then that gravity is altogether missing in the middle because it needs a superclassical notion so that it's not a perpetual motion machine doing work always for free. That these theories need to be built up again and revisited, their assumptions that went into them, because these ones that were put aside for a while or at the time to say that thus we have an absolute of the ideal of our relative theory fixed and free of considerations that would distract or simply are negligible in the usual case, that what remains are considered the dominant terms in the infinitary expressions, which have the analytical character that survives, that reflects that the analytical character is the result, that these kinds of things make for that having to try to re-explore them when the non-standard and the non-standard and non-standard of the analysis is buried way underneath us and then just stacked upon all this way up. It's a pretty thorough undertaking to try to figure that out. Mostly so it demands having it set up from the outset that these kinds of things, like looking at Aristotle and how he arrives at his opinions and his debates that he has. He's a great grandiose hedge. He's also firmly opinionated to arrive at authority. Compared to something like Schopenhauer, who's like, I'm going to entertain everything. I'm going to entertain you. I'm going to entertain myself. Everything is fantastic, and I've got it covered. And as far as I can tell, I'll be happy to put it down in a way that I've philosophized it already, and now you can read it out. Schopenhauer is pretty great. And then for something like Cassirer, he's like, I can readily write this out just like Schopenhauer does. And without going too much further in the details, and the Hispanic is like, we really need to rewind a bit, and then whether or not that's to be associated with anything at all that's more than the teleological is not a given. That's the super scientific in a sense, super sensuous and supernatural. That it is yet the merely teleological and not necessarily theological is yet supernatural. That said, that the mathematics has a lot of ways to approach it for the foundations that then do arrive at the fundamental theorems of what then are these descriptive theories. So to arrive at the fundamental theorems of calculus, the fundamental theorems of algebra, the fundamental theorems of arithmetic. And these most usually related to prime factorization, to the derivative and integral, to the roots of polynomials, and those being the fundamental theorems, usually things. There's then lots of other features that become possible in the higher geometry, as Graustein puts it. And with regards to like theorems of Pappus from geometry, which help to show that there's certain very particular things that are profound, the way they arrive past congruence. Everyone should learn congruence at some point and be utterly astonished and then perfectly pleased that it's so satisfying, is geometric convergence, congruence. That on either side of two intersecting lines are angles, and they're the same angle. This is the affine, that meaning that it preserves angle and proportion. That two triangles are congruent regardless of side length, that their angles are the same, and thus this congruency is in geometry. That's the congruency of kind of like an origin. And then when the theorems of Pappus and the 9-point theorem and these various theorems kind of show that now in an area, it's began a tiling, or it's began something that's further repeated and makes a regularity. It makes beyond the metric, which is like the notion of that there's a measure, there's a length 1. Around this origin is the norm that throughout the entire space is the same regularity. So these notions of congruence and then higher congruence in a sense, but regularity and regularity and regularity again, and those being complementary besides that they're each a piece kind of easy to carry out in an inductive account, makes it so that it has to be pulled back together, that there's always the thorough and thoroughly deductive account. because otherwise it's possible to make one from these combined inductive things that tear each other to bits, that arrive at each other's contradictions, and not with regards to a contradistinction that makes for two things and then making a synthesis of them together, which is then what arrives at a correct form of reasoning, instead of just allowing these ideas that would otherwise just be less and less and less of the one, making it more and more and more grand, which is good when you only care that that's so it carries out, and you can just call it closed, done, and with the stroke eliminated and reduced and canceled, the result something that it is a done thing, it's a fate, it's an opus, it's a work. That this other idea that the necessary fuller contingent also provides all the super classical and extraordinary stuff, and then it also can show that then some of the inductive accounts which are meant to arrive at the same thing are themselves incomplete and partial, and not really saying so, and have proved their own stipulation in that sense. So the logical circularity here is with regards to the circulus logicus virtus, this virtual circle of going around and turning things over, versus the vidiosis, the vicious circle, which is just proves itself, which has got no justification for doing, yet remains in its own way non-self-contradictory, if so merely saying something that is something to which it actually attaches the relevance that it should. So that's kind of my usual idea of these things. The graphical example of this we've been talking about, or has been talking about the past couple weeks, is to take a circle and you draw a diameter. So the diameter is vertical and there's a circle, and it's a unit circle. And then with regards to the circle, there's the diameter, and then so you divide it in two, and then you draw two circles centered on that. So their diameters are half the diameter of this outer circle. And then in each of those, you can further accomplish this same thing. And the idea is that the perimeters of these circles is that the sum of their diameters is the same as the outer diameter. So the sum of their perimeters is the same as the outer perimeter, because it's pi times d. That's the whole perfect thing about a circle, is that it relates the quantity of something that goes around in the area, pi, times d, the diameter. So p, the perimeter, pi, and d, the diameter, are related like this all the time. So no matter how many times you subdivide these diameters into two circles and their perimeters of their diameters ad infinitum. So a billion and a trillion and for all these higher order numbers, which we have words and 10 to the so many, the perimeter of all those circles that can be drawn on that line and the outside one are the same. Yet in the limit, it's a flat line, and it's not the same. So inductively going forward, at each case where there's a subdivision, it's the same. But in the infinite limit, when it completes, it is not the same. And then that's a graphically accessible example that the limit of the sums of the subtracted areas is the area of the circle. So what's left is just a line segment in the middle. There's nothing left but a line segment in the middle, and its length is only the diameter. Whereas the division of the refinement of those curves with regards to either pole of the circle, the diameter, and each one of those is like a yin-yang ad infinitum all the way down, that it just goes to show that then would be a limiting case saying like it's so for this one and the next one ad infinitum. Yet it's not so in the infinite when it's really complete. That just goes to show a great counterexample to otherwise that induction can complete itself, because it can't. And when it's kind of to be arrived at, that induction arrives non-self-contradictorily of a thing, it's because a greater deductive account provides that. And here that's with regards to usually the geometric series in Zeno's expositions. So these are the books. This is about the rough plane, that Euclid's plane is smooth and flat, and Poincare's plane is rough and flat. And that what that intends to entail is kind of like the ideas that the rationals and irrationals form, a grain to this otherwise smooth, real valued continuum. That's what it's kind of figured into the Zollfire metrics. And then this collocation was as of something relating to the account of the hypercube distance equals 1 and all what that could be and what those would box out to be about something like the terms and the interpolation operators. Here is with regards to an implementation, polynomials, remainder terms, to give the desired estimate, that this makes just examples of this in one space term, what those dimensional quantities would so combine to be, so that there would be a method here using the quadrature and the parabolic forms to arrive at how then that falls most naturally to solve for what those would be given these various conditions. So that was considered pretty relevant to the hypercube distance. See, here's the Dictionary of the History of Science. Let's find an entry from them today. Oceanography, isotope. Stimulated by Prout's hypothesis, 19th century chemists and physicists vacillated between interpreting atomic weight values as evidence for or against the complexity of elements. In 1888, William Crookes speculated that elements might really be aggregates of two or more different atoms, each varying slightly in mass. In a very different context, chemists working on radioactivity, radiochemistry were puzzled as to where to place the phantom-like decay products of radioactive elements. By 1913, some 30 radioactive elements had been identified. To save the simple elegance of the periodic law and avoid its implication of as many different elementary species as atomic masses, Frederick Soddy, in 1913, defined isotopes, Greek same place, as chemically identical atomic masses occupying identical positions in the periodic table. That isotopes of non-radioactive elements might also exist was triumphantly demonstrated by F.W. Aston between 1919 and 1930. Aston also used the concept of isotopy to explain Prout's hypothesis. Isotopes soon proved to be of immense practical value. According to their atomic number, how many protons they have is how many electrons they have, so that's how they behave according to chemistry. Pioneered their use in analytical chemistry. Hevesy used them as tracers in biological and medical research, and Hughes deployed them in investigating the mechanism of chemical reactions. The great success of stoichiometry and electron physics and the quantization and quantum mechanics and the whole principles of the theory and all these ideas that go into making a theory of it, when it's really still kind of as yet operationalist and instrumentalist, that we only have ratios of these things to other things, all finally is kind of boiled down by like mass is gravity according to, weight, and there's only like three defined units: the length, the time, and the degree Kelvin, and everything. There are many empirical units that yet remain, between those being just like the last three SI, Standard System International units. That is so. Hidden variables. Any set of hypothetical physical quantities, knowledge of whose values would permit more precise predictions of the results of measurement on a theory, on a system than the statistical predictions of quantum theory. One historically important reason for postulating such quantities was to avoid quantum indeterminism. Orthodox interpretation of quantum theory denies that hidden variables exist. Indeed, it denies anything exists except the objects of the theory. And so the idea that the continuum mechanics is what arrives at that, instead of just defining otherwise particles to exist out of thin air, as it were, is one of these things that kind of separates these theories a little bit between like the minimal theory, which is good because it's a severe abstraction, and that's all you have to collect in the computation. And then like a more principled theory is that there are more principled theories than that. Nevertheless, several theories incorporating them have been proposed, notably by David Bohm. It's been claimed that quantum theory is inconsistent with the existence of hidden variables, and various proofs have been offered, including an early and influential proof by John von Neumann. Other physicists, including Werner Heisenberg, claim that at least contemporary hidden variable theories yield no new experimental consequences, give merely inferior restatements of quantum theory. These days, they call it oftentimes supplemental variables, because hidden variables had gotten so put down by these eminent figures that it was considered kind of like a poisoned well. But this wellspring of these ideas that are associated with Bohm and de Broglie and the real wave collapse, these kind of things, have seen a great resurgence in the past few decades. And indeed, it's often so that hidden variables just assume part of the predictive and deterministic and real content of the system in these quantum mechanics. The situation has been clarified by work since 1960, notably by J.S. Bell. Although one can construct a formal hidden variable model of any quantum system, there are reasons for believing this cannot always be of physical interest, either as an interpretation of quantum theory or as a potential successor to it. One of the reasons to believe that there are always these implicits that fulfill all the rest of the stuff, because this theory of quantum mechanics has at least one either random variable or numerical method, or, and for example, it's got quantum amplitudes that are these, or it's got analyticity could fall out after the complex analysis. There's another one of these things in the nonlinear. There's any number of ways to establish that the quantum approach of quantum mechanics is only at best partial. So there's always a formal account for at least some hidden variable because it's got an error term. And so to not acknowledge that at least some of parts of these systems of mechanics have non-zero, if negligible, according to the partial mechanics, these things in their completions, has that there's always a hidden variable, and it's even usually nominally non-zero, even if under sufficient criteria it can be assumed to be close to zero or vanishing, or they can be assumed to be inconsequential or negligible. It's still not that way. There's always an extra, because the derivations of this mathematical of this theory, which the authors of these particular points seem to leave out as being given by the theory, what this actual mathematical definition is supposed to say, is not what it says. So it's important to look at that and be able to say, well, I see you're using Bayesian priors and your quantum amplitudes, and then as with regards to your Hamiltonian and these Bra and Ket, that then you just handed this whole thing off to Feynman as a series of connective dots, and it's like these dots are connecting the waves. It's like, yeah, that's because they're waves. So that's just something to be said. Although one can construct a formal hidden variable model of any quantum system, where the predictions of any physically plausible hidden variable theory must diverge from those in quantum theory, experimental tests to date are usually interpreted as having favored quantum theory. Yeah, they are. Hindu science. The most spectacularly successful of the sciences in ancient and medieval India was linguistics. Vyakirana, analysis or variformation. Linguistics acted as a paradigm for the methodology and style of expression of other disciplines, especially in such fields as logic and philosophy, fulfilling the role which in the West was taken by mathematics and geometry. Well, this is interesting. I hadn't really thought of that. There's been some talk here before, of course, of the development of language. I've been reading a lot more of that Watmo's language, and it's just an example of that words can be communicated in intersubjective only insofar as they exist and they have enough definition and can be conveyed in a brief enough time and conveyed in a manner which has the comportment of both that which is so and that which is profound and that which is always enlightening and that which is forever a constant. That linguistics is a great thing. So the idea here that in the 4th century BC, there's a fulfillment of a tradition of grammatical study, which is already ancient in this day. It says that 8 chapters of just under 4,000 short rules, these sutras, consist on brief statements. So maybe this would be like Peter's sentences or something like that, 1,600 years later. Compared to the Western tradition, Panini's grammar is far more like post-Chomskyan language descriptions. So here we have Tesnier for dependency grammars because it's really quite a thorough account of the natural language and its richness. Compared to Chomsky's grammars are like, this is the simplest grammar, this is the next tough simplest grammar, this is the next tough simplest grammar. These ones are too hard because most everything that people have as a regular conversation over the course of the day is at least one of those, not those. So then I'll have to check into Panini's grammar. being entirely generative in his method, while the Caracca, participant in an action theory of the semantics of case, nominal suffixation, and sentence syntax, is frankly transformational. The whole rests on a thorough understanding of the principles of phonetic description and morphological constituent analysis. The techniques so successfully applied to the study of language, especially the concept of economy and method and the adoption of a technical terminology, taken over by several other disciplines. It's occurred naturally since Sanskrit has always been the medium of Indian scientific writing, so any young scholar had first of all to undergo a rigorous training in grammar before moving to his chosen specialty. So yeah, that's interesting to say that our language of mathematics is in those terms, and the language of words is in the terms, and science has its own language as well. And so some kind of basic language or interlingua or lingua glossa, kind of like the linguan being Latin and the glossa being Greek, in terms of interlingua being like language that can be understood by everybody, with something like Esperanto is a Romance language kind of defined to deride to make logban or whatever it is as a portable language. Vis-a-vis this basic language is British American scientific industrial commercial, and the way that lingua angla today is global for sure. It has that then the idea that once a term mathematically or scientifically has been used, that can never be changed really, and that has a whole discourse about it, is a great thing. And so that has here for like this geometry and number theory, and then arithmetic and algebra and analysis, and then function theory and topology, having all the different variations in those, because everything else is fixed and cannot be changed. And it's because they have identities and they have values, and the names we have for them are perfectly apropos. And then to get then in the infinitary and the non-standard and the superstandard and the extraordinary, that it goes to show though that the study of language and having formal grammars is a great account of something that's relevant. And then it gets into more of the history, just as kind of as was considered a little bit here between the various readings from the histories and the studies of the philosophy about the centers of development of the Indic. So yeah, this book has got a bunch of great little sections, like the section here on hermeneutics and hermeticism. Hermeneutics is kind of like after Hermes Trismegistus, or like Mercury or Thoth and all that, kind of like this is our study of the truth of knowledge. And then like hermeticism though is kind of like a different kind of thing. The mysticism and what as what kind of like in the cargo cult, his usual kind of association is like there once was a tribe of a primitive culture, and then one day an airplane landed on the field, and it was a great formative event. And so then since after that, and it left a bunch of cargo behind, which were great value of goods. And then after that, they for a long time they maintained the act of setting up a runway in case it would come again, the cargo cult. And so some of these aspects of mysticism are variously. One is kind of like the esoteric and the inner tradition, and the other it's kind of an emulation on the face of things without really a reason why. So yeah, hermeneutics and hermeticism are two different things, but they both mention Hermes Trismegistus. Mercury or what, and that Athena or Minerva, the ancient avatar of post-Atlantean wisdom, as after Zeus, she just sprang out of his head like a full-formed thought. And so that's just something that in the dictionary of the history of science, that's something that historians of science know about. Logos 2000. What is today about? Well, it's a period of time. It's 24 hours is a day. 86,400 seconds by definition, according to our usual timekeeping apparatus. This is a book by Robert Sachs called Nuclear Theory from 1953.
So we got a lot out of reading the Heisenberg with reading the Einstein and Heisenberg in his introduction and preface about the history and things go into it. So in 1953, there is a lot going, desire to keep the length of this book within bounds has therefore resulted in the neglect of a number of interesting matters. Among them such topics as nuclear fission, the liquid drop model, the theory of angular correlations of radiations from nuclei, forbidden beta transmissions, and so on. This is beta decay as a continuous process. So like when we were talking about the quantum mechanics and hidden variables and that being all finite and particles and pointwise and finite and particles and pointwise again, and saying nothing about hidden variables, has that the author here references things that are so related. Well, this is nuclear physics though. So they were like, well, they're not talking about quantum mechanics anymore. That's nuclear theory. But it's all considered one thing, so it is. Particular emphasis is placed on the two-body problem. And then the two-body problem is so classical because it affects to describe proportional to a quantity of two bodies' values, either their opposite charge or their like mass. And according to the distance between those two particles, there's the force proportional to the product of their quantity and inverse proportional to the square of their distance. This is the two-body problem. So how do they fall together or orbit each other? So the idea is instead of that they always are being pulled and will fall together and will be pulled together, the idea is that they're always orbiting each other and then that they'll reach each other this way. So nothing ever kind of goes in a straight line with regards to that because there's an entire universe around them and it would have to be entirely contrived to make it so that they were totally perfectly balanced on either side. So there's always a non-zero part of the straight line connecting them as they draw together, like two magnets will just go right together until they click and they've reached a stasis and are together. And similarly with that, then the three-body problem is like, well, when you have three different things pulling each other together, then how would that be constantly, changing the focus in the middle? The idea is like, well, they're always rotating outside as they form like their own independent rotating frame. That this is kind of the way of things, and why the many-body problem is so difficult to solve is in a sense because it's kind of framed from the wrong end of the telescope, in some ways. For one, the experimental facts are on the whole susceptible to simple analysis. Hence, these facts are discussed in detail. It has been impossible to keep the discussion exactly up to date. The detailed analysis is to be taken as a consistent approach to the interpretation of the data rather than as the final word on the subject. Well, I hope you've had a great day today. And it's kind of goes in the course of these studies that it's foundations and it's a thorough account. It's for the 21st century, and as a theorist, it's really just what I want as having the best theory, because there's a lot that comes of it is like, well, if this is great thinking, then is it really just that it's kind of like a mental currency to have these kinds of ideas and bring forward? It's like, yeah, it is. So that way, at least it's easy to explain to people. It's like, oh, I can see why he's doing that. He thinks it's in his self-interest. Vis-a-vis also, of course, that it's great to think that it also gives. It's the great giver of everything that arrives at the results of science in a longer kind of account. Happy holidays.